All right, let's start. We're going to be solving LeetCode's weekly contest 361. So let's start with question 1. Here's the link. It's called count symmetric integers. You're given two positive integers, low and high, and an integer x consisting of two n digit is symmetric if the sum of the first n digits of x is equal to the sum of the last n digits of n. So half the digits sum is equal to the next half of the digits. And it is required that the number of digits is even, which is assumed here, and return the number of symmetric integers in the range low-high inclusive. All right, so this is uneasy. We get a few examples, but the important part here is that the bounds are at most 10 to the 4. So there are, at most we need to check 10 to the 4, 10,000 numbers, and checking whether a number is symmetric is pretty fast because at most the numbers will have 5 digits if it's 10 to the 4. So we go over the digits and we check these conditions. So the number of iterations is bounded by 4 times 10 to the 4, which is 40,000, which is a very small number in LeetCode. So let's go that route, the brute force route. This pattern of problem is pretty, hey, smart coder, how are you? So this pattern is pretty common. You have you're given a range and a condition. You want to count the numbers in the range that satisfy some condition, and the easiest way to do it is just to implement the condition independently, go over all the numbers, check if the condition is satisfied, and that's what we are going to do. So we'll go over all the numbers in the range, inclusive, so we have to add 1 to the upper bound in Python. And then we're going to add, let's do it this way. We are going to add 1 if the number is symmetric. So now this boils down to checking if the number is symmetric. And for that, we're going to need the digits of the number, the base 2, the decimals. So this is how we usually go over the digit. I guess you could also convert it to a string, but I like to do it this way. Notice that it doesn't matter whether we go from most significant to less significant, because we only care about the number of digits, and then the two parts, it doesn't matter if it comes first or last. So let's not worry about that. In this particular case, we're adding from the least significant digit. I think that's called the little Indian problem. The little Indian versus big Indian. Most significant, yes, big Indian. But in terms of bytes, but in this case it doesn't matter. But yeah, little Indian sometimes is more useful because when you want to add long numbers, you want to go from least significant first. but that's just a side note. It's not necessary for this problem. Okay, so first we check if the yes, we get the digits of n, and if the length is odd, then it is not symmetric. And then let's divide it by 2, and we need the sum of the first k has to be the same as the sum of the last k. And this should work. Let's try with the examples. It's right and accepted. Cool. Yeah, I didn't think about any edge case, but yeah, I don't think it is necessary actually. Okay, so how do we do this faster? This is the part where we try to optimize. We try to do a follow-up that is not needed in the contest. This is what you should do in the contest. So how do we do this faster? Let's go to the drawing board. And so one thing that we should notice is that the numbers, the range is, the numbers have to be between 1 and 10,000. Okay? And the number of digits has to be even. This number has 5 digits. This number obviously has 1, so there are only the number of digits has to be either either 2 or 4. Those are the only possibilities. So it seems that there are not many numbers that satisfy this condition. For example, let's take the case of 2 digits. So for the numbers to have the same sum, both digits have to be the same. So the only numbers in this case are 11, 22, 33, so on up till 99. So there are 9 numbers, symmetric numbers of 2 digits. And then the case with 4 digits, so we can think of this number as formed by a, let me see, as formed by 2 numbers. So 100 times a plus b, and a, and both of them. So what are the ranges of these numbers? These numbers have to be, so a has to be, can't have any leading zeros, so it must be in this range. But b can have, it could be even 0. So let's think about this. So if we need the number of the sum of b, of the digits of b, and the sum of digits of A to have to be the same. So maybe we can go over all this. Notice that this range is included in this range. So maybe you can go over all these 100 numbers, 100 candidates. And we get the sum of the digits of the digits sum of B, and we group them. We group them by the sum of the digits. So once we do that, we know that we need to consider all the pairs that are in the same group. And that way we can generate all the numbers that are symmetric without going over any number that is not symmetric. And it seems that there are few of them, but let's check it out. I don't see how we could compute that easily without writing a program, so we can try it out. So let's leave this here because it might be useful. So the goal is to pre-compute all the numbers because they're very few, and then just use that, because I think this is run. The class is called for every test case, but this is run only once for execution. So like we said, let's group them. Let's group all the numbers that are in this range that we said was this. So we consider all the A's and all the B's, and we want, so these numbers have at most 2 digits, so it's easy to get the sum of the digits, and we append the number. So that's useful. So let's consider first the ones that have 2 digits. We said that there were 9 of them. And yes, these are the 9 possibilities. And now we want to go over the groups, the numbers that are in the same group for each group. So let's call this G in groups values. And then we want to consider all the pairs in the group. But for A, for the most significant part of the number, it must be greater than or equal 10, because it cannot have leading zeros. And then for J in range, same thing. Is this a scalable solution? That's a good question. So for 10 to the 9, you would have to add at least the number of digits 6 and 8. This is a little ad hoc. I'm not gonna lie, it's a little hacky. No, this is just to learn. I mean, I know it's not very useful, but I mean, it's a quick way. It can be handy to know how to do this kind of things. But I mean, I'm I'm getting there. Be patient. So here we have g of I is a. So we said that this would be 100 times g of j. Okay. So now we computed all the numbers. Let's check it out. So symmetric, and let's even look at them. So there are 624. That's what my intuition was, that it was very small. So now we can do something of the sort. So we go over. So these are not necessarily ordered. So let's say that we go over all the numbers, and here we check that they are within the bounds, and they are, no, well, we don't need to check this anymore. So that works. Accepted. And seems like it ran faster. I don't know if I have the run time. 70 milliseconds. Okay, distribution chart is not available here. But we can even do something a little bit faster. We can sort them. And we can do, yeah, we don't need to print them anymore. And we can do binary search. Why not? So bisect right of high, bisect left of low. I think that's it. Yeah, I missed the thing that we need to search for. Okay. So now it's a little faster. "39 milliseconds instead of 70. Anyway, so yeah, this was kind of a curiosity, if you will. It's I mean, you don't need to make these observations, but being good, improving at making observations is a good skill to have for problem solving. So that's why I think it could be useful to exercise this kind of thinking. Even though this solution is pretty non-general. But let's do, now that you, yeah, it helped. Now that you challenged me to make something work with bigger numbers, I'm gonna stand up to the challenge, and we're gonna do some digit dp. Oh, so this is the solution. Okay, we're gonna do some digit dp. Yay! So how do we do digit dp here? It's a little tricky because so the conditions here are depend on what number of digit it is. So once we generated the number going over the digits, which is what you do in digit dp, I left and move on. Yeah, this is something that you do after the contest, not during the contest. Okay. So I think we need to know what the size of what the number of digits are going to be, so that you know whether the current digits it's in the first half or the second half. So we are going to do the recursion for each number of digits. In this case, like we said, it's 2 and 4, but this could be extended to 6 and 8 if the bound was 10 to the 9, as you suggested. And so okay, so let's start. And again, when you have something, you need to generate numbers in a range. You can generate the numbers up to high, from 1 to high inclusive, and then subtract the numbers from low -1 to 1. Yeah, probably. Yeah, I think you can do even that. So that's why I'm standing up to the challenge. So let's start doing this. So we're gonna have a count. Well, let's call it C to make this smaller. Okay, so C. So what parameters? So we're gonna need the bound, the upper bound. Then we're gonna need, like I said, the number of digits. So yeah, let's call this upper bound, number of digits. And then we are going to have the index of the current digit. Initially, it's going to be 0. And then we're going to have the sums of the two parts. So I'm writing this in Python, actually. I wanted to do this like a mathematical formula, but never mind. So, and there's another catch that we need to, I think I used this trick in a previous digitdp stream, but I think we need to also remember the number of leading zeros, because once we get to the number of digits, we should not count the leading zeros. So we need to make sure that the leading zeros are 0 at that point. So let's do this as well. And so there are a few. Are you following this? So maybe I'll write the code directly, because I'm writing it anyways. The params again, yeah, I'll repeat it while I write them in the code. I think the only tricky one is the leading zeros. The other ones are straightforward, I guess. So we're gonna have a count function that it's gonna have the upper bound and the number of digits, and then we want to subtract the number of symmetric integers up to low -1. That's the upper bound of this call, and the same number of digits. And we want to do this for the number of digits in the range, let's from 2 up to 6 exclusive, and the step should be 2, and we're gonna add up this. And so we're gonna do a recursive memoization. This is the upper bound, so we want to count how many numbers there are less than or equal to this upper bound. Then we want the number of digits to be ND. Then we want the index of the current digit, which is initially 0, from least significant to most significant, so that we know when we reached the total number of digits. And then we're gonna keep the sums of the least significant half and the most significant half. So this is going to be initially 0 and 0, and then we want to know the leading zeros. Why do we need to know the leading zeros? To make sure that we comply with the number of digits, because if we have, when we finish, when I is equal to ND, you mean this one? Yes, we can, but I think it's a little easier to write if we do it this way. So yes, it could be S1 and S2, but I think it's a little bit, because we're gonna have an if statement depending on the value of I to know if we're in the lower half or the upper half, and based on that condition we're gonna set both of these values. So if we have them separate, I think we'll have to repeat the if statement. That's why I'm doing it this way. So now, well, this is as usual. If the upper bound is negative, then we know that there's no number. Okay? And then if we reached the number of digits, then here we need to check the condition. So yes, we need to keep the leading zeros because of this case. If we are in the digit index number of digits, we have concluded we generated the number, but if it has leading zeros, then it doesn't really have the number of digits that we wanted. So we need to say no, there's 0. We messed up, and we shouldn't count this number because this number doesn't have ND digits. That's the reason. Let me write it down. So the condition if is the leading zeros must be 0, so that I is the effective number of digits, and then and also we need to make sure that we need to check the condition. So now this means that we comply with both conditions. The number of digits is ND, and the sum of the lower half digits and the upper half digits are the same. So in that case, we found 1. And if that's not the case, then it's 0. We haven't found 1. Cool. And now, as usual, we try all the possible digits. So all the possible digits. And we're going to add the counts for all possible digits. And here we go. So the upper bound, as usual, we subtract the current digit. We divide by 10 because this is base 10. Then, so maybe I can format this way. I don't know. No, let's keep it in one line. Okay, so then the number of digits doesn't change. Then I goes to the next digit. So, and then the sum. Here we need to know if we are in the first half or the second half. So that's going to be if I is greater than or equal, I is 0 based. If I is greater than or equal half the digits, then we're on the upper half. And if we are on the upper half, we want to add the current digit to the second component. But if we are on the first half, we want to add the current digit to the first component. Tuples are immutable. Yes, that's intentional. I'm not changing the tuple. I'm creating a new one. And this is intentional because I'm caching this function, and caching requires the keys to be hashable and mutable. If I use a list, the lists are not hashable because they are mutable. So yeah, that's intentional. And here, if the digit is a 0, then we have to increase the number of leading zeros. But if it's not a 0, then the leading 0 resets to 0. So I think this is all. And we get the right answer. And accepted. And 53 milliseconds. So yeah, this is not, I mean, it's faster than the version that did not use binary search. But, well, the advantage is that this would work, as we said, with very big numbers, with 10 to the 18 bounds. So why is that? Let's see what the... Except the way you calculated the S. Yeah, let's go back. So the condition, so yeah. So I is going to go from 0, 1, 2, so on up to nd minus 1. So it's 0 bases. When it's equal to nd, then we finish. That's the base case, okay? So these are going to be the... So nd, we know that it is... so let's see a more concrete example. So if nd is 4, then we're going to have 0, 1, 2, and 3. So 4, so this is the cutoff. So nd, when it is 4 divided by 2, it's 2. So this is the cutoff. So that means that if I is greater than or equal the cutoff, we are in the second half. But if it is not, if it is less, then we're in the first half. And S0 corresponds to the first half, and S1 correspond to the sum of the digits of the second half. So that's why, and we need to create a new tuple because of what you correctly pointed out. Say nd equals 4. 1, 2, 3 is not valid. Well, I think I covered that. So, okay, so this is the condition that I explained. If this is true, we're in the second half. So that means that we need to update, to add the current digit to the second component of S. This is the first, the 0 index of S. And this is the index 1. So we keep the same values. This is just making a copy. We keep the same values, but we add D to the second position. And likewise here, we add a digit to the first. So is that clear? Yeah, perfect. Okay, cool. Yeah, let's make sure this is not hard if you know what you're doing. That's why we got it on the first try, because we thought through what we're doing, and in that case you can prevent mistakes as much as possible. All right, so yeah, what I wanted to do was to think about the number of sub-problems. So yeah, so upper bound, this one is always tricky, but let's say that this is, so let's call the total number of digits, right? Which can be, let's say that is up to 19 or something like that, in the case where we have 10 to the 18. So upper bound, let's say that it's roughly the number of values. Let's say that it's roughly 20, which is, I mean, it's hard to calculate exactly because we are dividing by 10, but we're also subtracting 1. So maybe I should think about this. I haven't thought about it. I usually assume that it's roughly proportional to the number of digits, but maybe I could compute it more precisely, but I'm not going to do this right now. And the we know that it's so the number of values of nd is approximately d and a half of d. Then I has the, well, the number of values of I is roughly d, and the sums are, so here we have another d for the leading zeros, and the sums are going to be, so at most you have, if you have all 9s, you are going to have so 9. So let's round it to 10 to make it easier. And so the total sum must be 10 times d and a half squared, because we have two sums. So that's a bound. So in total we have, so let's say 20, let's say it's 10 to the 1.5 times, we say this is 10 times 10 times, this is 10 10 squared times 2 times to the 4, and this is 10 again. No, 10. So yeah, we said 10.5, and here, did I miss one? So this corresponds to this. This corresponds to this. This corresponds to this. This corresponds to this. So I'm missing one. D. And so in total we have 3, 4.5, 8.5, 9.5. So yeah, it's not, yeah, it's a little slow for this number, but for 10 to the 12 it should work. Yeah, I'm not sure if so I'm this is a bound, an upper bound, but I'm not sure if it's tight because I'm not sure these are all independent. Well, they might be. But anyways, let's say that it works for up to 10 to the 15, something like that, maybe. I'll have to recalculate to be sure, but I think we spent enough time on this problem. Let's move on. Otherwise, this is going to be too long. Yes, we already spent 45 minutes on this. So let's move on. So let me share. Let me share this one. Thank you. Yeah. Yeah, I had to think about this. This wasn't easy to come up. Well, I guess when you have experience, it was very important to learn the leading zero trick. I hadn't used it before that stream. That's why I'm learning myself when I do these streams. That's one of the reasons I do them. So let's close this and let's go to this problem. Cool. So minimum operations to make a special number. We're giving a number represented as a string which has at most 100 digits, and you can pick any digit and delete it. And if you delete them all, the number becomes 0. And you need to return the minimum number of operations required to make num special. And if it's considered special if it's divisible by 25. Does not contain leading zeros. Does that matter? I don't think so. So we get this example. So here we delete this 2, 5, and 6, and this is supposed to be a multiple of 25. It's divisible by 25, so we only have to return this to delete this 2. That's the output. Here in example 3, we delete the 1 and we get 0. And 0 is always a multiple of every number. For every integer. Okay, so this boils down to divisibility rules. That's a common, I think this is taught in school usually, in high school or something. So for example, the divisibility rule for dividing by 2, you check that the last digit is even. By divisibility rule by dividing by 3, the sum of digits to be divisible by 3. Divisibility by 4, the last 2 digits should be divisible by 4. Divisibility by 5, the last digit should be either 0 or 5. So these are all these rules that if you know how to derive them, we can see if there's one simple rule for 25 as well. Maybe there is. Let's check it out. So how do we find these rules? So yeah, in school maybe they just gave you the rules to memorize them, and they came up from the authorities. But here we need to understand why. So we have a number expressed in digits in decimal digits, base 10. So you can always express a number in terms of powers of 10 and their digits. So let's say that we have this number. How do we do this? I print this. Yeah, I guess you can always try to, but as you still need to prove that. Anyway, so let's do this. So you have a number. So let's say that you have a number that is that has digit 0, digit 1, digit 2, and so on, and it has n minus 1, a number of n digits, n minus 1. So this can be expressed as a sum of 10 to the 0, the unit digit, times d0 plus d1 times 1, and so on up to the n minus 1 and n minus 1. Okay, and how do we check divisibility? We want to know what this number is. We don't know what the digits are. Could be any digit. We're considering all numbers, but we want to know the remainder when divided by 25. So notice what happens if you. So let's write another one, which is important. You'll see why. D2. So 100. It's obviously a multiple is 25. It's 25 times 4. So that means that we can cancel this out because we know that this has a factor of 100. So it's going to be a multiple of 25. So that means that the remainder, this is 0. But all the bigger powers of 10 also are divisible by 100. So then they are divisible by 25. So we can cancel all of them. And that means that we only care about this. Well, this is 1. We only care about this. So what does this mean? This means that we only check a number is divisible at 25 if and only if the last two digits considered as a number as another way to express this would be in this notation here would be d1 and d0 mod 25. So this has to be 0. This is the same equation. This is an equivalent equation. That's why if and only if this is true, then the number is a multiple of 25. And yeah, and notice that if we change this by all the rules that we learned are derived by the same process. For example, if you have 4 instead of 25, then you'll notice that it's exactly the same thing, because the first power of 10 that is a multiple of 4 is 100. So you cancel out the exact same terms and you end up with this same formula. That's why you only check the last two digits, the most significant digits, the two most significant least significant digits. So yeah, so now we have derived the divisibility rule by 25. So what do we do now? So we can try them all. We can try them. There are only so finally, for this to be true, we have only a few cases. So it's 25, 50, or 75, or 0. So the number, so let's say that it is a number that is that has at least, it's greater than or equal to 100. So the last two digits have to be 00 or 25 or 50 or 75. These are the only options. Yeah, I do this because there's a special case. We're putting a leading 0, which is weird, but I think we need to do that in this problem. Okay, so let's code it. So we're gonna try all the so one option would be to remove all digits that are not 0. That's going to be our default value. You can always do that, and that keeps you 0, which is a multiple of 25. But now we're going to try not removing all of them. So we said that these are all the possible endings of the number, and we're going to update the maximum, and let's say that we call this the cost. We're going to have a helper function, the cost of getting the number to have this ending. So we're going to do this like this. We're gonna, yeah, let's do it the little Indian way. So m mod 10 is the least significant digit, and m divided by 10 is the second most significant, least significant digit. So we want the cost of these digits. So with this tail, we call this the tail. So we're gonna go over the number from least significant, and we want to remove if a digit does not match the corresponding digits on tail. So j is going to go over the digits of the tail, and I is going to be, or maybe we can just go over the digits. So from least significant is the reverse order. We want to map it, we want to parse it as an int for convenience. And so we have two options. The current value of the tail matches the current digit, or it doesn't. If it doesn't, then we need to remove it. So we add 1 to the result. But if it matches, then we consume it. So we need to increase j, and maybe we have matched them all, in which case we return. So if j is equal to the length of the tail, we have matched them all, so we return res. And if we have not matched them all, then we cannot make the number have that tail, so we return infinity. Okay? So we are being deterministic about why we only use deterministic. What do you mean by deterministic? We're being rigorous by proving why we only need that. That's what I would say. None is not, so where is this? Oh, so we are returning none. Oh, okay. Inf, so why are we returning? Oh, so this is min. Okay, some typos. 231, 231, let's go. Accepted, cool. So did you follow my logic? So what we're saying is that the number either has this tail, which is based on these four options. The number either has this tail, which in the case of 0 means it has a tail of 2 zeros. And that is what we are searching for here. We get all the tails. We compute the cost, which could be infinite, in which case, in the case where we cannot get that tail. And there is a special case in which the number, in which we want to convert it into a 1-digit or 0-digit number. So here we're assuming the result is going to have at least 2 digits. And here we're covering the case in which it has either 1 or 0 digits. Okay, so when it has 1 or 0 digits, it has to be 0. And to get 0, we need to remove all the non-zero digits. And that is the cost. So, and then when we want to match the tail, this is just like matching. This is just a matching kind of problem where you want to match a subsequence. You keep track of the index on the needle, as it's called sometimes, and the haystack would be the number, and we are going from least significant to most significant in both numbers. And when we find a match, we consume the value of the needle, and if we match them all, we found a solution which has this cost. But if we don't match it, we need to add 1 to the cost because we need to remove. So res is the number of deletions or removals that we do. And if we get here, it means that we could not match it all, so we cannot get that tail, so we return infinity. This is never going to be the answer because we already have a value here that is not infinity, so we're always going to skip infinity. So do you think that's clear enough? So this is the proof of why we only care about the tail, the 2 last digits. And what I said is that this argument works for all the divisibility rules. So for example, for the divisibility rule of 3, so your solution is different. I'll check it out later because I'm a little bit I want to get to the the last one is a tough one, so I'm gonna spend some time on that one, I guess. So for example, if you want the divisibility rules of 3, here it is different because you know that 10 has remainder 1 or is 1 mod 3. So that means that all the powers, any power of 10 greater than 0, so all the 10s can be replaced by 1, so this is always true. So that means that this becomes d0 plus d1 plus d. So the powers of 10 are cancelled or are removed. And that's why when you want to know if a number is divisible by 3, you just add the digits and check the divisibility by 3 of the addition of the digits. So this argument, it's a framework for deriving all the divisibility rules of this kind of, well, this is base 10, but of course it could be other bases as well. You only need to find one of these conditions that makes you simplify, makes you cancel. Sometimes there is none. For example, for 7, you are going to eventually get a cycle, because when the potential reminders are from 0 to 2 in this case. So eventually when you multiply by 10 and you go over all the powers of 10, eventually you're gonna get the same reminder, which is going to repeat. And So you'll always get some kind of rule, but it could be complicated. Anyway, so let's move on to the next. Let me share this. And yeah, this is linear, of course, and it's the best you can do. So count of interesting subarrays. You're given an array nums, an integer modulo, and an integer k. Your task is to find the count of subarrays that are interesting. And a subarray is interesting if, so let count be the number of indices in the range. So in the subarray that are equal to k mod modulo. And yeah, I'm not sure why they give you the index here. They could say just the values in the subarray such that they are, yeah, that indirection is unnecessary. And then you do another modulo on the count of values, and you also want them to be equal to k mod modulo. Okay, a little tricky. Return, so you have to count the number of interesting subarrays. And the usual definition of subarray, non-empty. This is usually bolded because it could be both ways. Yeah, I guess it's hard to say, to count how many empty subarrays there are. Anyways, or there's only one. So the length is 10 to the 5, which means you cannot do a quadratic solution. The numbers are pretty big. All right, so this is this kind of problem where we are counting, yeah, we're counting subarrays. I did a problem that was also this kind of problem recently, which I'm gonna share the YouTube video for that problem. It was a little more complicated because it used bit masks, but yeah, the idea is to think about prefix sums. So if you think about it, this condition binarizes the values of the array, right? Because so there are values that are equal to k mod modulo, and there are values that are not. So that's why there are two kinds of values. You could change it. You could change the array. I don't think the values matter actually. So this number is a little useless, I think. So let's try that. Let's even do it explicitly. Why not? So for e in nums, e mod modulo equals to k. So now it's a now it's a Boolean list, and we want to count all the subarrays that have true, have a number of truths that are k mod modulo. Okay, so we can keep track of the number of subarrays we want to keep track of the number, the count of truths in a prefix modulo modulo. And that way, we're gonna have a two-sum kind of problem where we have an equation, but it is a modular equation. But it's pretty much the same as the two-sum problem. This problem appears all the time. So let's say that we have the count. Well, let's say that we have the count. So what's the problem? The count for the right index. This means that we are counting how many truths in our modified array we have in the range from up to right inclusive. Oh, well, let's do it more mathematically. In this range, we have the sum. This is the sum that belongs to this range, and let's do it modulo modulo. So for the subarray to have this condition that is equal to k mod modulo, the equation has to be of this kind. We need the count up to right minus the count up to left. Let's say that left and right are inclusive, so we want left minus 1, and this has to be equal to k modulo modulo. So this is an equation, a modular equation. So we're gonna go over the right pointer of the subarrays that we care about. So this is fixed. This is a constant, right? And this is an unknown. And k is also a constant, which is given. Modulo is also a constant. So we have an equation with only one unknown. So let's solve it. Let's just add this over both sides. And then this is exactly the same as two-sum, but modular arithmetic. So the count of left minus 1 is going to be equal to this modulo modulo. So we compute this, and this will give us the remainder that the count left should have. There could be more than one, of course, but we want to count them all. And how do we count them all? Quickly, we keep track of how many there are for each remainder to the left side of the right. So that's how we can count them quickly. Notice that left could be minus 1, right? Because we said that left and right was an inclusive an inclusive interval, so left minus 1, it's the empty prefix, which is going to have count equals 0. So we need to have this special case so that it all works out. That means that the reminder 0 is going to have one occurrence at the beginning of the iteration, because we're going to start from right from 0. Let me show it in the code. Okay, so let's do what we said. So we're going to keep the count in res. We're going to have the the count of how many there are for each reminder to the left of right, which initially it's the prefix we said it was 0 for index -1, and there's only one of them. So then for right in the range, we're going to keep track of the count, as it is called, for right. So the count for right, it's going to be increased if nums. So how do we call this instead of nums? Because it's not nums now. It's if it's good, I don't know. If it's good, then we count it, but we want to count it modulo. And now, so yeah, let's do this exactly how we. What are you? I did not understand your comment. So this is the count right, but we want to know the count left, or left. You would left -1. Okay. Well, let's say that it is. Let's call it like that. Whatever. That converts a good array to zeros and ones, so we can use it to increment. Oh, I understand what you're saying. Yeah, that's cool. And so yes, I don't like that this is not exactly left as if we defined it. So let's call it prev of left. And so we said that this was going to be count right minus k mod modulo. And now we want to know how many there are. The count from the reminder. These are the number of lefts that the count pred left modulo, and that's it. And now we need to add count right plus 1. Let's see if it works. Runtime error, key error. Oh yeah, this could not be. This could not be in here. Could it be? Yeah, I know that I could do that, but I'm a little confused because in my previous solution, I didn't do this. Yeah, I think, yeah, I know what I did. Yeah, but because even this is not gonna work, yeah, it's better to use a counter. But thanks for the comment. Yeah, 3 and 2. And accept it. Cool. So yeah, this is a very standard problem. It's two-sum with modular arithmetic and with the prefix sums twist. Let me share the link to my submission. So that is two-sum modular arithmetic two-sum with prefix sums. All right, so let's get to the tough one. Minimum edge weight equilibrium queries in a tree. That's a mouthful. There is an undirected tree with n nodes labeled from 0 to n minus 1. You're given the integer n and a 2D integer array of edges. So you have weights. It is weighted. And you're also given queries, which consist of an A and a B. Find the minimum number of operations required to make the weight of every edge on the path from A to B equal. One operation, you can choose any edge of the tree and change its weight to any value. So here we have a clarification. Queries are independent of each other. So if you have to change something to solve one query, then you reset. You don't keep the changes to the next query. Returns to the initial state. And then distinct is a sequence of distinct nodes. Starting from, yeah, so this means that it is a simple path. So in trees path, there are unique paths between simple paths between nodes, and those are is the shortest because it's the only one. Return an array answer of length m. Okay, so you need to compute every query. Okay, so here we get some examples. There are 7 nodes. six edges, and this is the graph, the tree, and the queries are, so for example, this query means that you need to go from 0 to 3, and they are already all the same, the edges, the weights. So this is 0. Then from 3 to 6, all 2, so it's also 0. You don't need to change anything. From 2 to 6, 2 is here, 6 is here, so you have to change the 1 into a 2. That's the optimal. And then from 0 to 6, which is the whole thing, so you need to change either the 1s to 2 or the 2s to 1. Is the same, it cost is 3. All right, so I think that clarifies the problem. So notice that I could very easily know the minimum number of changes. Why? Because you're gonna keep one of the labels. These are not. I don't think it's useful to think about them as weights, because we don't have to add anything. That the quantities don't matter in this problem. We can think of them as labels. So you're going to, when you do all the changes, you're going to keep, you of course want to take advantage of one of the labels and save some changes by keeping those as they are and changing all the others. And then the cost is going to be the number of edges minus the number of edges in the one that you keep. And of course, you want the maximum. You want to keep the maximum. That's going to minimize the changes. So that means that the minimum cost is going to be the number of edges in the path minus the maximum number of labels of the same label in the path as well. So we can't forget about this minimization. We just need to count the number of labels that there are of each label in the graph. So there are only a few labels. So then how do we find the paths quickly? So the numbers are big. We have up to 10 to the 4 nodes. And, well, roughly the same number of edges as with any tree. And the number of queries is up to 20,000. So you can't do anything quadratic. You can't go over all the nodes or all the edges for each query, because that's obviously going to be too slow. You need to do something quicker. So here's when, so to find paths on a tree quickly, there are several techniques. One of them that I explained in a previous stream is called binary lifting. So I'm not gonna go over all the explanation. I'm gonna share the link so that you can check it out later and learn about the technique. But what this gives you is you can compute a table that lets you compute the kth ancestor of every node in logarithmic time pretty quickly. So for example, if you are here at 7, if you want the first ancestor, that means that you go to the parent 0. But if you want the second ancestor, for 7, you're gonna get 3. Or if you want the third ancestor, you're gonna get 1, which is the root, and so on. And you can do that quickly. So that's like the primitive operation that we count on. But how do we use that to get the path from one node to another in the tree? Well, I mean, if you root the tree somewhere, let's say that this is it doesn't matter which one is the root. We can say, let's say here one is the root, the root. You need that to determine which one. So when you talk about ancestors, you're going from a node to a path to the root. That's how you go over all the ancestors. So that means that the tree must be rooted. Here, the tree that you're given is not rooted. So we can choose any arbitrary. I guess in the code we're gonna choose 0, which is convenient. But in this example, we can look it in this way. So notice that the paths from one node to another in a tree, they go through what is called the lowest common ancestor, the LCA. So for example, here, if we want the path from 5 to 4, if we go from 5 to the root, we go up the tree to 2 and to 1, and we do the same to 4, from 4 to 2 to 1. 2 is the first common, the lowest common ancestor, or the first when we go up in that path. So all paths can be decomposed this way. Even if we find, for example, if we want the path from 2 to 4, or from 4 to 2, here the lowest common ancestor, the LCA, is 2, which is one of the nodes. But so they all follow this decomposition. You go from one node to the LCA, and from the LCA to the other node, and that's going to be the single path in the tree. And the ancestors that we calculate with binary lifting are going to let us find this LCA pretty quickly. So let's go to the board. How do we do that? So let's say we have some. So let's say this is the LCA. We want to go from A to B. So we have here a path. Yeah, let's say this is A and this is B, whatever. So the way we are going to do this is, or let's say the way to do this inefficiently is to just check the depth. Let's say that without loss of generality, that the depth of A is greater than or equal to the depth of B. Then we can move up from A to the parent and so on until the depth is the same. One step at a time. Okay, and now we get to a situation when they are both in the, well, this is not an edge, this is a path. but we know that the depth is the same here. So now we move them in this inefficient way. We move them both at the same time, and that means that eventually we're gonna get to the same node, and that's going to be the LCA, and that means that we have covered all the edges on the path. So we can count how many labels we go over the whole path, and we can count how many labels there are in all the edges, and then we apply that formula that we mentioned to find what is asked to respond to the query. Okay, so this is a way to do this slowly, because since we are moving one edge at a time, there could be 10 to the 4 edges, and that's not gonna not gonna cut it. So for example, so we have 2 steps here. First, we moved A up to the same distance, but with binary lifting we can move. That's exactly what it does. It moves a number of steps. We get the kth ancestor, so we call the depth of A minus the depth of B, which is a non-negative number, and we want the dth ancestor of A. And we can do this quickly with binary lifting, as you can see in the so we use binary lifting, and we find this quickly in logarithmic time. So now we are in this situation. How do we do this moving up with both nodes quickly? Well, remember that in binary lifting we know how to do jumps of powers of 2. So we can somehow binarize the path to the root from both nodes by checking if A is equal to B, right? Because at some point they are going to converge to the same node, and then the path from there to the root is going to be this common. So if you think about it, when you move up, at the beginning we know that B and A, let's say that A and B are different at the beginning. Then when we move up, at some point they're going to be the same. That could be at the root, if the root is the LCA. But so that means that this is a monotonic sequence, which is, so we're basically going to do a binary search to find the highest node where they are still different. Okay, and that means that if we go to the parent of each at that point, we're gonna find the LCA, and we're gonna finish going over all the edges in the path from A to B. So that is all the idea behind the solution. Let's now code it. It's not hard. The only thing is that the time limit is a little too tight in this problem. So for Python, I had to do some optimizations to get it to pass. And so And I think the one that made the difference was to just well, I'm gonna tell you now when I write the code. So okay, so let's begin. So remember that for binary lifting, we're going to create a table that says how many so that gives us the ancestor, the kth ancestor for powers of 2 for every node. Okay, so but we want to know how many powers of 2 we need. And that means what is the highest power of 2 that is that we could want to jump. Okay, so we are going to call this log, and let's say that we want to find. I'm doing this because you usually hard code a number, but I want to make this as fast as possible. So log is going to be the size of the table. So that means that we're going to have the power of 2 to the 0, 2 to the 1, 2 to the 2, up until 2 to the log minus 1. Okay, so let's say that initially the size of the table is 1. So we only have 2 to the 0. We only make jumps of size 1. But we need to make jumps of at most n minus 1, because that's the maximum number of edges that you will need to get from a leaf to the root. Okay, if the tree is degenerate, so the maximum number of edges is n minus 1, and you might have to traverse them all. So if the next power of 2, the one that is not in our current table, is still less than what we might need to jump, then we increase it. And so that's going to give us the biggest power of 2 that we're going to need. Then we also want to know the maximum label, okay? Because we want to avoid having more than we need. Yeah, I guess here we could even use some kind of index compression. I don't think it's useful, because one idea is to just check the maximum, but maybe we can use some index compression. So we go over all the W's and we ignore duplicates and we sort them and we enumerate them, and then we have the index and the value. We create a map from the value to the index. So let's call this W. And then we have an index, and the number of indices is going to of different values is going to be the length of this dictionary. And now we want to create an adjacency matrix in order to traverse the tree. So the adjacency list of U, we append B and the index W of W, and the same from, this is undirected, so the same on the other direction. Okay, so now we have the adjacency list, we have the sizes, we have normalized or compressed the labels, and so I'm doing this compression just to make it as quick as we can. I think it matters in LeetCode because I think they are testing the time, they're timing the whole execution of many cases. So if we can make cases that have a sparse labels faster, I think it counts to the total. Anyway, so then we're gonna have, we needed the def here that we're going to initialize with -1 to use it as for marking nodes when we traverse the tree. And then for binary lifting, you're gonna get the ancestor for every node. This is the table that I was talking about, and for every power of 2. And then we're gonna have another parallel table for every label. So this is also going to be for every node, and then for every, because whenever we make a jump, we want to count how many times each label occurs in the path that we're jumping, so that we can also not only we go quickly to the ancestor, but we also count the counts for every label of that jump. So here we, for every power of 2, and then for every label. And now we want to do a BFS or DFS, whatever you like. I prefer to do, I mean, I don't want to do it recursively because that's slow in Python. So I'm going to do a BFS, which is easier to do iteratively, or it must be. So we said that the root is going to be, so to count the depth, to set the depth, and to set up the ancestors with the parents, we need to traverse the tree from the root. So we are defining here that the root is going to be 0. And we want to set up initially the depth of 0 as 0, depth of 0, because it is the root, and the ancestor, this is a trick that we can use, the ancestor of the root, the first ancestor, which is index 0, which means 2 to the 0, which is 1. So the first ancestor is going to be the root itself. So we are creating a loop so that we don't go out of bounds when we jump to ancestors. Okay, so then we go. So we do a normal DFS here. BFS, breadth first. So if the depth of the adjacent node is -1, it means that we haven't visited yet. So we want to update its depth as the depth of its father, its parent. plus 1, and then we want to set up which parent it is. So again, when we use 0, that means we are talking about the parent, and it is u. And then we want to count that in the count of the values of the labels for this situation, we want w. So we are considering here we are considering the edge from B to U, which is its parent, and that edge is labeled with W. So that means that here we are considering that edge from B to its first ancestor. We want to count 1 for the label W. All right, and then we do the usual. We append B to the Q. So now we have initialized def. We have set up def, but we still need to set this up for values greater than 0. So how do we do that? We just go for I is going to be the power of 2. We already did this for 0. So we start from 1 up to log, not inclusive. And so the ancestor of, well, we have to do this for every node. Well, another way would be to do this right here. So we only get into this condition, into this block, the first time we see a node. So since here we are initializing the index 0 of these tables, we can just initialize it here. So for node B. So the ancestor of B of I is, this is explained in the binary lifting video, and we want the ancestor of B of a jump that is half I, and then we want to jump half again. So we do 2 half jumps. Since these are powers of 2, a jump of 2 to the I is equal to 2 jumps of 2 to the I minus 1. And the first jump is from B, but the second jump is from the I minus 1, 2 to the I minus 1 ancestor of B. So that's why that works. And then for every label, we want to count. We are going to do something similar to this, but for the counts. So the count for this, the count of edges with label W from B with a jump of size 2 to the I is the count for B jumping from B but half the jump. And then we want also to count the other jump, the jump from the ancestor of B I minus 1, and again it's half a jump, and for W. So that is going to give us the count of the number of edges with label W in the second jump. And now this is a condition, something to break the loop early, because this then ends up being the critical part of this algorithm. So we're doing this for every node, and there are up to 10 to the 4 nodes, 10,000 nodes. And then we're all going over this that is at the most 14. And then this is at most 26. So those multiply, and we're doing accesses to lists. So this turns out to be the critical part in terms of runtime. So we're gonna, so here we are jumping increasingly to the I, okay? But it could be that we already jumped to the root or past the root. And if we already consider the root, then we don't need to keep jumping higher. So if we are considering a node that is a child, that the first ancestor is the root, then we don't need to keep going we don't need to keep jumping farther and farther, because we're always landing on the root, and it makes no sense. So if the ancestor of b of I is already the root, which is 0, then we break. And okay, so now we have all that we need to compute the queries. So let's do the queries. So we're gonna have this many queries. Yeah, I guess I was, yeah, let's do it this way. So queries consist of A and B, the nodes in the So let's add a special case here. I mean, I'm not sure this is needed, but if they are the same, because there's an edge case where the tree is only one node, and in that case, the only queries that make sense are from that node to itself. And in that case, the answer is obviously 0. So you don't need to remove any edges in that, you change any edges. So let's handle that just to make sure we don't spend too much time on that query. So now when we looked at the algorithm, we assumed that the depth of A was greater than or equal to B, but that might not be the case. So let's force it. So if depth of A is less than the depth of B, we swap them. Okay, so now we know that the depth, and we want the diff of the depth, because we want to move up from A up to, and let's make sure that the difference is positive, is not negative, okay? It's because, I mean, it's obvious, but it's a check that we got the depths right. Yeah, I guess it's not even, yeah, it doesn't make sense because we are already, yeah, let's not do this. Okay, so we want to move up, and we are going to count the edges, the current number of edges, or yes, the edge count for each of the labels to solve this query. So now we're going to move up from A this many times, diff times, so that they are both at the same depth. And so now we apply the algorithm that we learned in binary lifting to, so we decompose diff into powers of 2, and we check if it's on, if a power of 2 is on in the binary representation of diff. And in that case, we jump for that power of 2 represented by this exponent I. And we want to check for we want to update the counts for every label. So the edge count of label W, we want to add the count from A, first the node, then the jump, the size of the jump, and then W, the label W. And we move to the ancestor, the 2 to the ith ancestor of A. Cool. So now we are at the same level, and we already counted all the edges for each label. And here we can assert that the depth of A is equal to the depth of B. All right. Just to make sure that we did not mess up that, we are assuming that at this point. So now let's check if A and B are different. Because if they are not, then we have already traversed the whole path between A and B. But they don't necessarily. We know that they are at the same depth, but they are not in the same node necessarily. If they were, that would mean that that B is the LCA. And we're gonna do something here to keep, well, what we said in the whiteboard, but finally A will be equal to B, and it will be the LCA. So then we will do what we said before, which is the sum of the edges no template. Oh, yeah, I'm coding all from scratch, if that's what you mean. So the sum of the edge count for each label minus the maximum edge count for any of the labels. So that's going to give us the number of edges that we have to change, or the response to the query, to the current query. So now we have to solve this, and we are going to do what we said. We are going to do a binary search, but it's a binary search in terms of binary lifting, in a sense, because we want to go from the biggest jump that we have up to the smallest. And we have the condition that we said. We said that we binarized the sequence, the path from the current depth out to the root. And it depended on whether we are, whether the ancestor of A is different than the ancestor of B for this jump, for the current jump. So in other words, the ancestor of A, if it is different, then we're gonna make the jump. Ancestor of B of A. So whenever we make a jump, we need to, well, at the end, we're going to make the jump. We're gonna update the nodes. But we need to count the edges. So for every label, we want the edge count of W and the jump on A from A and the jump from B of size 2 to the I. And then, so when we finish this loop, like I said, we're gonna be at the highest depth where A and B are different. So we need to move up one more time. And we need to kind of repeat this, but for 0. I guess we could write a function for it. Well, never mind. No, this with the loop. We need to move 1 up, but I it's gonna be 0 here because that means jump to the parent. And I guess this is it. Let's see if it works and if it's fast enough. Okay, so some typos are expected. Ancest, where is ancest? Yeah, I meant ancestor, thank you. Oh, here it is. List indices must be integers, not or slices, not list. What did I do here? So this is line 42. Did I use A and B before? Oh, this enumerates doesn't make sense. Yeah. Okay, so we got it right for the examples. Let's try our luck. Let's see, maybe TLE, maybe not. Accepted, cool. So we got it right on the first try. That's good. Hey Goku, happy Sunday to you. GG, thank you, Smart Coder. Thank you for bearing with me. It was a long one, a lot of code, but pretty good, I think. So yeah, I think I had to. I think this condition was the one that sped it up a lot, and also not doing recursion, because initially I did a recursive DFS to traverse the tree. That was a rookie mistake on my part, at least for me, because I know that you should skip, but usually in LeetCode it doesn't matter. That's why and I think DFS is a little shorter to, recursive DFS is a little shorter to write, so that's why I prefer it. But yes, in this case, you want to avoid recursion. And then this condition is pretty, like I justified it by explaining, because yeah, I had to do a profiling for this code to do C profile, and that's how I learned that most of the time was being taken by this part of the code, the setup of the tables of the count and ancestor table. And this is how I optimize it, by saving some cycles. Usually when you find the critical part, the part that is executed the most times, then you can do some small tweaks that are worth it to... this is just reducing the constant factor of the runtime, not changing the order of complexity. But sometimes you need that when you think your algorithm is good enough in terms of complexity, but you're still getting TLE, then you have to do some what I call micro optimizations, or some heuristic, some favorable or average case improvement, given that in LeetCode they seem to be timing all the runs for all the test cases and not independently. So that means that the average case matters. In any case, I think these optimizations even make sense in terms of order, because you're doing it for all the nodes in the tree, so you're always going to be for some nodes you're always going to be breaking early. I don't think it even doesn't matter what the shape of the tree is. Anyway, so yeah, I think it was a cool problem. I don't think I couldn't participate because of the time of the contest, but I don't think I would have gotten it in the contest because of the TLE. But oh well. It's a lesson for next time. It was a learning opportunity, and so that's it for now. This ended up being too long because I went over too many solutions for Q1. So it's been 2 hours and 15 minutes. So I'm gonna cut it here. Let me share the link to the solution, and I'm out. See you on the next one. Thanks a lot for watching.